strong base titration in terms of what's going on a molecular level when the titration takes place, and an overview of the calculations involved, and this will be up to the equivalence point. So we're titrating a weak acid with a strong base, and we are going to be pretty much only showing the predominant species in solution, the things in high concentration. So for example, HA is a weak acid. It dissociates very little. There's a few HAs that are dissociated, and we're not in general going to be showing those. So before you start the titration, before any titrant has been added, you simply have a weak acid in equilibrium. And this is a thing that's been done before. The weak acid doesn't dissociate much, but it does a little bit. And again, we're generally not showing the small amount of dissociated species. So very little of this happens, but there's a few. So out of maybe 100 molecules of HA, one of them or so will dissociate into A-, the conjugate base, and the hydronium ion. And in general, we're not showing those, but there's a little bit of it there. And this is a thing you've done before. You set up an ice table, you have the initial concentration of HA, it dissociates a little bit, and at equilibrium you have slightly less HA and small amounts or small concentrations of A- and H3O+. You set up the equilibrium constant expression, plug in things in terms of X, do your solving, and remember that K sub A is a very small number, so X is going to be small by comparison to the HA concentration, which can help simplify your calculations. Okay, now let's do the actual titration. So if we start adding hydroxide to the weak acid solution, hydroxide ions are going to encounter weak acid molecules, HA. They'll grab onto the H+, make a water molecule, and essentially the reaction that takes place is HA reacts with OH- to make the conjugate base A- and H2O, and the water will then go into the background, and essentially you're taking an HA molecule, and the strong base is converting it into the conjugate base of that HA molecule. Okay, so continue the titration a little bit more. Some more hydroxide comes in, finds more HA molecules to react with, removes the hydrogen ion, converts the HA into its conjugate base. And let's pause now and take a look at what's in solution, because we want to calculate the pH at various places. So here would be a good place to try. And we can track what's happened. In terms of molecules shown in this representation, we started with 6 HA molecules. We added 2 OH- ions, and the reaction is a 100% to completion reaction, so this will take place until one of the reactants runs out. In this case, there's less OH- than HA, so you'll run out of OH-, and we will end up having 4 HA molecules left at the end of reaction. We will have formed 2 A- ions at the end of reaction. That's what's represented here. And now if we look at what we've got, we have a weak acid and its conjugate base in solution. And a weak acid and its conjugate base, if in solution, if the two concentrations are not too far apart from each other, is a buffer. And we know how to calculate the pH of a buffer using the Henderson-Hasselbalch equation. And so it's just a make sure that you have the K sub A value for your weak acid, get the concentrations of the weak acid's conjugate base after reaction, which was what we just tracked in that reaction table, and you can calculate the pH. Okay, we keep titrating, add more hydroxide, reacts with more HA, turns it into or converts it into its conjugate base. Now we have 3 HAs left, 3 A- is formed, and we'll do a little bit more, and now we have a 4th HA reacts with OH- and is converted into A-. And let's stop again and take a look at what we have. And once again, we'll track what happens in terms of moles. This time we started with 6 HAs and we've added 4 OH minuses. And it's going to react until we run out of something. Again, it's going to be the OH minus, so HA and OH minus will both decrease by 4 molecules, or 4 ions in the case of OH minus. A minus will go up, 4 of those will be made, and at the end of the reaction we have 2 HAs left. We've used up the OH minus, we have 4 A minuses produced, and that's at the end of the reaction that takes place. And now we look at what we have in solution, and what we have in solution is 2 HAs that haven't reacted, 4 A minuses that have reacted, or sorry, have been formed. So we have a weak acid in this conjugate base. That's a buffer once again, because the concentrations are fairly similar to each other and significant. And we can once again determine the pH at this point of the titration using the Henderson-Hasselbalch equation if we get our HA and A minus concentrations, which we can determine from the amounts left after reaction. Okay, and if we keep on titrating, more HAs converted into A minus. At some point, maybe here we have so little HA minus that we no longer have a buffer, or at least the buffer calculations aren't accurate. We can always do a calculation with the case of A expression and normal equilibrium concepts, but we're still before the equivalence point. And then if we do one more HA reacting with OH minus, we have converted our last HA into its conjugate base A minus, and at this point we're actually not before the equivalence point anymore. We have reached the equivalence point, and that will be the subject of another video. Okay, done.